evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course being conducted by Department of Mechanical Engineering, IIT Guwahati. And we are into the fourth week of this course. And the theme for this week's discussion is normal shock waves, a very important topic as far as the compressible flows are concerned. The instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati, and I am a research scholar here. So we shall wait for a couple of minutes to see if somebody joins. After that, we will start our session. All right. Okay. Thank you. Okay, so I believe we can start this session. And I have slide uh, cough and sore throat, so kindly bear with me. Mm. So, normal shock waves. Uh, in this week's content, we have two lectures, lecture number 10 and lecture number 11. All right. So, discussion revolves around normal shock waves only. How do we model these normal shock waves and how the properties change across these normal shock waves? So all these things have been discussed in these lectures. So then there are topics related to these lectures, and then there are a few questions. So we shall see these one by one. So introduction to shock waves. In introduction to shock waves, so we have been told that it has a finite thickness, this shock wave. It's a very thin region, all right, of the order of 10 raised to power minus 7 meters. And there is, and then there is abrupt change in flow properties across a normal shock wave or across a shock wave. Okay. Then subsonic versus supersonic events. So this in one of the previous lectures also this has been discussed. So how the acoustic wave moves and how the body that is producing this disturbance moves. So how the scenario looks like. Okay. Then characteristics of supersonic events. So this has been discussed. So here it has been told that the energy of your compression of the gas is taken from the kinetic energy of the upstream flow. Okay. Then there is this very important topic that starts, which is formation of shock waves in one-dimensional medium. So it first starts with a compression wave. Okay. So this modeling has been shown by means of a piston. So let's say we have a cylinder and we have a piston. Now, as we change the position of this piston from here to here, let's say this is an infinitesimal change in the position of this piston, piston, tube or cylinder. What will happen? A pressure wave will propagate in the medium. Okay, so let's say we have some medium here, air we can take. Okay, so this pressure wave will move in this medium. Okay, so this compression wave will move. So this has been graphically shown this way. So upstream of your compression wave, this is the pressure. So in front of your compression wave, you have this pressure, and at the back of your this compression wave, you have this pressure, right? So we are discussing formation of shock waves in 1D medium. Now, what also happens is that the static temperature here increases. Okay, the static density here will also increase. Okay, so this is first. Now what we do is we again let this piston move. Okay, now we again let this piston move. So this now we earlier had this compression wave from our first movement, right? Now we are making this piston again move. So this will create another compression wave. Now regarding the velocities of these two compression waves, so this is from first and this is from second. So for the second your compression wave, the velocity will be high because this region, okay, this region at the back of your first compression wave, here the static temperature has increased. Okay, so this is there. Now, if we have a piston which we are moving from rest, okay, So scenario will be like this of compression waves. So you'll have a series of compression waves like this. This you call as head, this you call as tail. All right. And obviously the tail velocity will be higher than the head velocity. All right. Now if you see, because I'm saying the tail wave, the velocity of tail wave will be greater than the velocity of the head wave, right? So what is going to happen? At some point, these waves are going to collize, right? They're going to meet at some point, and this uh, point gives rise to a shock wave, right? So this is the merger of compression waves to give you a shock wave, right? Then there are normal shock waves. So normal shock waves basically are normal to the streamline of the flow, right? That is why they are called normal shock waves. There are oblique shock waves also. Okay. So let's say we have this wall like this, okay, which has diversion here. Okay. Now if your flow with supersonic speed moves, so it will move like this. And the shock wave that will form, that will be like this. Okay. So this is basically oblique shock. Then moving normal shock and stationary normal shock. Then your shock tubes. What is a shock tube? Shock tube basically is a tube where what you do, here you give pressure to a gas, you fill it with pressurize with gas. Okay. Here you keep a diaphragm. Diaphragm can be of aluminium or mylar or paper. Okay. So after some pressure, this ruptures. This diaphragm ruptures. Okay. So this then gives rise to a shock wave. Okay. So there are lengths defined. So what should be the length of this section and related to a driver section? What should be the length of the driven section? Okay. So this has been defined. So, so to attain a shock wave. Okay. So, but then what happens is this disturbance starts from here. Okay. It starts from basically this diaphragm and it starts travels. Okay. So this basically is a moving shock wave. Then stationary shock wave. So stationary shock waves are attained in your supersonic intervals. Okay. Where you keep a body in the test section. Okay. Then let the high pressure gas pass through this body, and then you study your flow physics, supersonic wind tunnels, right? Mm, okay. Then there are fundamental equations of normal shock wave. Fundamental equations. So let's see what are the fundamental equations of. First is your continuity equation, which is this. Second is your momentum equation. So these are fundamental equations for your normal shock wave. Then moving on to questions. Please read this question and try to answer this question. Later, I'll discuss this. So, question says that which of the following is not an assumption to derive the fundamental equations for a normal shock? So, basically, these fundamental equations are applicable only with some assumptions. Okay. Now, what these assumptions are? So, the question is directing us to that. So, four options are there. First says that the frictional effects are negligible. Second says that the shock thickness is very small compared to dimensions of the stream tube. Third says that the flow processes, including the shock wave, can be considered to be adiabatic. Fourth says that the flow across the shock wave is considered to be unsteady. Okay. So frictional effects are negligible. This is true when we talk about assumptions for normal shock wave. So thickness is small compared to stream tube. So this is also true. So thickness of the shock wave and then the stream tube. Okay, the stream tube for which we are defining these fundamental equations. Then third says that the flow processes, including the shock wave, can be considered to be adiabatic. Okay, so no heat exchange. So this is also an assumption. The fourth says that the flow across the shock wave is considered to be unsteady. So this is not true. The flow is considered steady. Though the changes are abrupt, okay, steep changes are there, but even then the flow is considered to be steady across the normal shock wave to get the fundamental equations of it. So D is the correct answer to this question. Now please read the next question and try to give an answer in the comment box. So the question says that for flow properties across a normal shock, which observation is false? This is what the question asks. So which observation is false? For flow properties across a normal shock. Says that velocity decreases, the total pressure decreases, static pressure decreases, static temperature increases. So if we talk about a stationary normal shock, okay, this is there. So here you're across the normal shock. Your mag decreases, your density increases, your temperature increases. So this happens. Okay. So also your pressure definitely it increases. Your static. So this is static, this is static, this is static. Okay. About your total pressure, so across the normal shock, there are losses in total pressure. Okay, so your total pressure is going to decrease. So velocity decreases. True. Total pressure decreases. True. Static pressure decreases. What about the static pressure decreases or increases? So if we say here static pressure increases. So in that case, this becomes the false statement. Fourth says that the static temperature increases. This is true. Static temperature increases. All right. So C is the correct answer to this question. So what happens to density across a normal shock? So I've just told you that static density increases. Okay, so A is the correct answer to this question. The normal shock waves, this has been discussed. This is lecture number 11. So this is from previous lecture only. Okay. Then we have Prandtl relation for normal shock. So it is like this. A star square is equal to U1 U2. Or M2 star is equal to 1 by M1 star. So this is Prandtl relation for normal shock. Okay. There are other relations also like this. Okay. So for further details on this topic, you can refer to lecture number 11. So link will be given in the description. Right. Then moving on to flow property calculation across a normal shock. So here Mach number relation. So this is like this. So across your normal shock, how the mm, Mach number decreases. So formula for that is this. Okay. So we can try one numerical on this, right? So let's say M1 is 4, okay, and gamma is 1.4 of air. Then M2 square becomes 1 plus 1.4 minus 1 by 2, 4 square, 1.4 into 4 square, so 1.4 minus 1 divided by 2. So this is there. So now let's calculate. So please calculate this. So let's say what we get as M2. Okay, so this is what I'm getting. Now, to what extent this calculation is correct, I'm not sure. So I have performed this calculation using my cell phone only. Okay. But the thing is that your Mac has come out to be subsonic. And in reality also this happens that across your normal shock wave, your Mac falls down to a subsonic value. All right. But in your oblique shock waves, this is not the case. So your Mac across your oblique shock remains supersonic only, but it decreases, right? So you can do this calculation and if there is something wrong, you can just type in the comment box. Okay. Then this was about Mach number relation. Then we have static density and speed ratio. So this is the relation for that. Okay. So this is static density ratio basically. But then when you see it with your continuity equation, you can get the speed ratio also across a shock wave. So which comes out as this. Right. Then okay. Other things are also there. Static pressure ratio is there. So this is P2 by P1, which is equal to this. Okay. We need a gamma and M1 for P2 by P1. Static pressure change across a shock wave. So this is like this. It's P2 by P1 into 1 by M star square. Now P2 by P1 you can get from here. M star square is this. Okay. So this. So this way static temperature and static enthalpy ratios. Okay. These can be calculated. So this is really Pitot tube equation. Okay. So this you can refer to the lecture. You can see there better. It's a long expression, right? Then across a normal shock, entropy change. So this is EP T2 by T1 minus R ln P2 by P1. So T2 by T1 we have seen this, P2 by P1 we have seen this. So using these relations we can get the entropy change across a normal shock. And in terms of total pressure change, because your total pressure decreases. So this is there. Okay. So these are the things. Then we will move on to questions. But before that, we will take a short break. After that, we will continue with the session. Thank you. Okay, so we can continue with the session. So now we will see questions that we have. So first we have this question. Okay. So this question says that Mach number across a normal shock is a function of dash and whether this second dash is required. For that, D option is there only. But if not required, then C one, two, three, three options we have. So the first option says that the Mach number before a normal shock. So so this is M1 and this is M2. So what is M2 function of? So this has been asked. So now for this, see this relation here. Two parameters are there. One is M1, other one is gamma. Okay. Now coming back to the question. So this is M1 is there. So specific volume is not there. Specific heat ratio is there. So both A and C are correct. Right. So this is your question number 4. Then what happens to entropy across a normal shock? So please now answer this question. So I was talking about question number 5. So here entropy across a normal shock has been asked. So for this, what has been done is, so I have taken this relation. Okay. So now I have taken natural log on both the sides. Okay. You can see this. Now because P naught 2 will be less than P naught 1, in that case this ln P naught 2 by P naught 1 is going to come as negative. Okay. So what I have done is I have taken, so I've reversed this P naught 2 by P naught 1. So what that will do is that will take a negative out. Okay. So that will take a negative out. Now on the right hand side, we have minus S2 minus S1 into R, right? So negative and negative will cancel out. So eventually we'll have S2 minus S1 is equal to 1 by R ln P naught 1 by P naught 2. So this is positive and ln P naught 1 by P naught 2 is going to be positive. So this suggests that your this S2 minus S1 is going to be positive. This suggests that your entropy is going to increase, right? So then this increases. Okay. Then we have this question. Please read this. So this is your m2 square. Now if you take square root of this will come out to be 0.475, right? So this is there, and then next question. Moving on to next question. So it says that oh, so this was in division. So this will be in numerator. So this question says that a normal shock wave is dash to the streamlines. So I've discussed it here that your normal shock waves are perpendicular to your streamlines, right? So for your question number 7, the correct answer will be C. Oh, this will be C. So specific entropy change across a normal shock is a function of static pressure ratio, total pressure ratio, specific heat at all of the above. Please try to answer this question. So let's go back to here. Okay, so you can see that it is a function of specific heat Cp also. P naught, this also, this also. All right. So all of the above. D will be the correct answer to this question. So please read this question. So P naught 1 is this, P naught 2 is this, R is this. S2 minus S1 has been asked that we can calculate. So putting the values, so if you calculate this, this will come out to be this is your question number 9. Then moving on to uh, last question of the session. So question says that static density and velocity before a normal shock are given as this and this. Find the value of velocity after the normal shock if the static density has increased to 3.8. So how do we solve this? So using continuity equation, you will solve this. Okay. So so this is the velocity. Okay then. So we will end it here only for this session. So I'll conclude this session. So this session was on normal shock waves. So we discussed a number of topics on normal shock. Okay. So there were two lectures. In first lecture, we learned the modeling part of normal shock waves. Okay. Also, we saw fundamental equations of normal shock and what are the assumptions related to those fundamental equations that have been presented. Then there are a few questions on that. After that, we saw lecture number 11, in which majorly the properties change across a normal shock wave. This was taken care of. So we saw across a normal shock how the Mach number decreases. Okay. Then your static pressure, static temperature, static density increases. Then your total temperature remains conserved or constant, but your total pressure decreases across a normal shock wave. Okay, which means there is loss in total pressure across a normal shock. Then about entropy. So entropy increases across a normal shock wave. Okay. So there are two relations that have been presented. And then questions we saw. The questions related to this lecture. So this is it about today's session. So coming session then again will be on coming Tuesday. Yes. Also before that, so one question was asked uh, by a student from lecture number 5, slide 12. Okay. So you were saying that so U star is this 2 gamma R T naught divided by gamma plus 1. Okay. Now gamma RT is basically A naught square by gamma plus 1. So your A naught will be then outside this root. So you will have this. Okay. So this is there. So A naught will be outside the root. So mistakenly in the slide, it has been taken inside. Okay. So as per it has been worked out in the slide, so it should be outside. Right. All right then. Next session again will be on coming Tuesday from 6 to 8 p.m. So this will be week 5. Till then, goodbye. Thanks for watching this video. Thank you.